In this video, I'm going to go over Dalton's law and the combined gas law. So this is page 14 in your packet. Dalton's law of partial pressures. And we can fill in this top here. It says the sum of the partial pressures of all the components in a gas mixture is equal to the total pressure of the gas mixture. So the way we could write out a formula for this, we could say P with that subscript of T. So that's total pressure equals the pressure of all the gases that make up that mixture. So we'll just write it as PA, PB, PC, and it's really just however many things make up that mixture. So you add up all those partial pressures, it's going to give you the total pressure. Remember, pressure comes from the collisions of the gas molecules with the walls of the container. So if each gas molecule is colliding with the walls of the container, you add up all those collisions, it will give you total pressure. Pretty easy concept overall. Now when you're doing problems with this, there's a couple different ways it could come up. So in this example here, it says a flask contains a mixture of oxygen, argon, and carbon dioxide with partial pressures of 745 torr, 0.278 atmospheres, and 391 torr respectively. What is the total pressure in the flask? All right, first thing that jumps out is that we have different units here. Two of them are in torr, one of them is in atmospheres. They all have to be the same, so I'm just going to take the odd one out and convert that. So I'm going to start off with this 0.278 atmospheres and convert that to torr. Remember, to do conversions in this, you have to figure out what are the values at standard pressure. We need those equalities. Standard pressure in atmosphere is 1 atmosphere, and torr is 760 torr. All right, you multiply 0.278 times 760, it is going to give you 211 torr. Since we start off with 3 significant digits, I round my answer off to 3 significant digits. And now what I could do is just add that to the other partial pressures. We have 745 torr, and we have 391 torr given in the problem. You add all of that up, and it's going to give you 1,347 torr. Now, I started off doing a multiplication. You go by significant digits, so I had 3 significant digits, so I wrote my answer in 3. Now, when you add, you go by decimal places. Since these are all whole numbers, I'm just going to leave my answer here as a whole number. The total pressure would be 1,347 torr. Another way these problems can come up is with percentages. Whenever you're working with a problem with percentages, think about, is the answer you're going to get going to be a larger or smaller number? Percentages are these things that I see every year students make a mistake on because they're just going a little too fast. So this is telling us that the total pressure of a mixture of helium and neon is 498 millimeters of mercury. So the partial pressure from the helium and the neon is adding up to 498 millimeters of mercury. So in terms of pressure, this should be the biggest number because that's after they're both combined. It's telling us helium is 20% of the mixture. What is the partial pressure of helium? So it's asking me for a partial pressure. So I should end up getting a number smaller than the total pressure. So that's telling me what I have to do now. I have 498 millimeters of mercury. To get a smaller number when you're working with percentages, you're going to have to multiply it. This percent you have to make into a decimal, so you just move the decimal point 2 places to the left. So you get 0.200. And when you multiply this out, 99.6, since this is 3 significant digits, that's 3 significant digits. I'm going to have my answer in 3 significant digits. You get 99.6 millimeters of mercury that goes along with the helium. Now this makes sense. This is only one of the gases in there. So neon must be making up the other 80%. And if we were asked to figure out neon, what we would see is that the millimeters of mercury, the pressure of helium, plus the pressure of the neon would add up to this 498 millimeters of mercury for the total pressure. But since it's only asking us for helium, I'm just going to stop there. Now, another way that pressures could come up, and this is what throws people off a lot of times. I'm going to scroll, if it lets me, to the next page. Number 8. Now look at number 8. Says the partial pressure of water vapor in a greenhouse is 139.0 millimeters of mercury, which is 18% of the total pressure. What is the total pressure in the greenhouse? So now this one is asking us for different stuff. It is asking us for total pressure. It's telling us that the pressure that it has here listed, 139.0 millimeters of mercury, is that 18% of the total pressure. So now when you do a problem like this, you should be getting a pressure that is larger than 139.0 millimeters of mercury. So keep that in mind when you're doing a problem like this. A lot of times people see a percent and a pressure, and they're just so used to taking percentages and multiplying them, but that would actually give you a smaller number. Remember, if it's asking for total pressure, your number should be bigger than that partial pressure that you're given. The combined gas law. Now, it says Choils here. Sometimes people come up with these things that help people remember stuff. The reason why it has Choils there, if you look online or something like that, sometimes people use that. It's Boyle's and Charles' law combined is kind of how people think about it sometimes. Other than right now, you'll never hear me say Choils again. This law could be used to determine how changing two variables at a time affects a third variable. This is the one where I was saying back when we started Boyle's law, we would use this equation, the one I'm writing now, to figure out 3 different gas laws. Remember, Boyle's law is if temperature remains constant. So the temperature is taken out of that, and you're left with Boyle's law, which is P1V1 equals P2V2. Charles' law is pressure remains constant, in which case the pressures are taken out of it, and you have V1 over T1 equals V2 over T2. Well, now the combined gas law is putting all that stuff together. P1V1 over T1 equals P2V2 over T2. You do these the same way that you would do Boyle's or Charles' law. You just have an extra variable now. It doesn't make the problem that much more difficult. You just kind of have to pay attention to what you're doing. I have a feeling. There we go. So I'll go over an example of this one with you. Now, after this video, I have 2 other ed puzzles that I'm considering as optional, where I go through more examples of Dalton's law and combined gas law. If you feel like you're good enough after this video to just get started on the packet work, that is fine. If you want to watch the other ed puzzles just for a little more help with that, that is also fine, but they're there if you need them. So if we look at this, a gas occupies 72.0 milliliters at 25 degrees Celsius and 198 Kelvin. All right, so I have these labels written down here, which I'm not always going to give you. What I was saying before is if you start labeling this stuff up here, it kind of helps to get in mind what kind of problem it is. So you have an initial volume, temperature, and pressure. It says convert these to standard conditions. What is the new volume? So we are looking for a volume. All right, so we can fill this stuff in. Initial pressure is 198 kilopascals. Initial volume is 72.0 milliliters. The initial temperature is 25.0 degrees Celsius. Now, just like we did with Charles' law, we have to convert this temperature into Kelvin. You cannot do the problem. Well, if you do the problem with it in Celsius, you will end up with the wrong answer. So since we're adding, we go by decimal places. 25.0 then becomes 298.0 Kelvin. All right, the pressure, P2. Now, it doesn't give us a number for P2, but it says standard conditions. So since we start off with kilopascals, I'm going to use the standard pressure for kilopascals, 101.325 kilopascals. V2 is what we're looking for. T2, standard temperature, is 0 degrees Celsius, which is 273 Kelvin. So now when I have all this stuff written out, I see I have 2 pressures, 2 temperatures, I have 1 volume given, I'm solving for another volume. The only way we can get all that is using the combined gas law. P1V1 over T1 equals P2V2 over T2. So I can start plugging these numbers into the equation. I have 198 kilopascals as P1. V1 is 72.0 milliliters. T1 is 298.0 Kelvin. P2 is 101.325 kilopascals. I am solving for V2, and T2 is 273 Kelvin. Now, you have a lot of variables going on there, a lot of numbers. The way I think about a problem like this, and you don't have to think about it the same way, but what I tend to do is, since I have all the variables on this left-hand side, I'm going to do all the math here first. So I'm going to do 198 multiplied by 72 divided by 298, and you're going to get an answer there. It's 47.8389 and a whole bunch of other numbers. Now, I'm not going to bother writing that down or rounding that off at this point, but I have that number, 47.8389, and that covers all of this stuff. Now, what happens, I want V2 by itself. So I know what I'm going to have to do, I'll write this in red, is I'm going to have to multiply by 273 Kelvin to get that to cancel out. And then I'm going to have to divide both sides by 101.325. Remember, what you do to one side, you do to the other. So once I get that answer of 47.8389, what I then do is multiply by this 273 that's on the bottom, because I want to get rid of that. So just at the same time on the calculator, multiply by 273. That gives you an answer of 13,060, and then a whole bunch of numbers after the decimal point. And while that's still on the calculator, I now divide by this 101.325 because I want that to cancel out. And now what I get as my answer so far is V2 equals 128.89. There's a whole bunch of other numbers after that. What happens, the Kelvin and kilopascals will cancel out because what I did to one side, I have to do to the other. All right, so multiplying by 273 Kelvin, dividing by 101.325 kilopascals causes those things to cancel out. The only thing that hasn't canceled out is milliliters. So my units are going to be in milliliters, but now that I have all this done, I just have to round it out. So I look at the numbers I have up here, the least number of significant digits, looks like 3, so I'm going to round my answer off to 3 significant digits. I get 129 milliliters. So that's it for Dalton's law and the combined gas law. Like I said, there are 2 other ed puzzles that are posted on Google Classroom that you can just find if you go in the ed puzzle. They are optional. If you want a little extra help, by all means watch them. If you feel like you're good enough now, you should be able to answer the questions in the packet.